chips break, discontinuous chips. Here promotes chip formation in positive rake angle. Chip formation giving the tool more wedge shape but weakens the tool section, causing heat concentration near the chip and reduces the tool life. And in negative back rake angle, chip is highly distorted, that forces increases tool vibration and chatter. No chatter and vibration in tool. These are major differences between positive rake angle and negative rake angle. We have to use positive for almost all ferrous and non-ferrous materials except brass and high strength alloys, and as well as brittle materials. In remaining places we have to use only positive rake angle. Next one is side rake angle, alpha S. So alpha S purpose is to guide the direction of chip flow. Earlier one is guide alpha back rake angle is also guide the direction of chip flow, and here to control the bending of the chip. Side rake angle is used to increase as the side rake angle increases, the amount of chip bending controls the chip bend. It controls the chip bending. So how it controls? As the side rake angle increases, the amount of chip has to bend decreases. Hence the power required to the part and the bend the chip decrease as the side rake angle increases. Heat generations will be high if you increase, as a fairly large part of power required to part and bend the chip is transformed into heat. The thickness of the chip is largely determined by the amount of feed per revolution. Here also again, carbide cutting tools, negative rake angle can be used, but it is almost always positive only. Negative very rarely we use. So side rake angle purpose is to bend the chip flow. Next one is end relief angle. This relief angle's purpose is to avoid the vibrations and rubbing action of cutting tool. End relief angle. End relief angle is used to avoid the rubbing action between edge of the cutting tool and the workpiece. So as the side rack end relief angle, sorry, this one is theta. So end relief angle increases, rubbing action decreases. The more the angle, up to a limit, it is better. If it is 0, then there is parallel line, so rubbing action will be more. Side relief angle. Side relief angle, the purpose is same as that end relief angle. Side relief angle is to avoid the vibration between the side flank of the, to avoid rubbing action between side flank of the cutting tool edge and the workpiece. So once rubbing action takes place, then that means vibrations will start. Once vibration will start, the machining won't take properly, so the surface finish will be rough. To avoid all this, end cutting edge angle, same as the end relief angle, but here also to avoid the rubbing action. End cutting edge angle. Between edge of end flank and workpiece. Side cutting edge angle. Side cutting edge angle is also the same purpose, but the thing is, it also controls the thickness of the chip. If you increase the side cutting edge angle, the chip becomes thinner and wider. It helps to avoid the built-up edge formation. Nose radius. Large nose radius causes chatter. So another system is, this is about American Standard Association system, ASA system. Another system is ORS system, orthogonal rake angle system. In this system, the angles are measured perpendicular to the angles are measured with respect to the plane containing the cutting edge angle. Principal cutting edge angle. The angles are measured with respect to the plane containing principal or side cutting edge angle and the plane normal to it. So designation for this is I alpha gamma gamma dash C lambda nose radius. So here the notation will vary from textbook to textbook. I is inclination angle. Alpha is orthogonal rake or side rake angle. Lambda is principal cutting edge angle. CE is auxiliary end cutting edge angle. Similar to gamma and gamma dash is relief angles. Almost everyone follows ASS system. Sometimes they give problems like convert the values are in ORS system. We have to convert the values angles into ASS system. For example, tan alpha B tan alpha S equal to cos CS minus sin CS cos CS tan I and tan alpha. So this is one of the matrix formula which is used to convert from one system to another system. There is another one, lambda plus CS equal to 90. So from using 1 and 2 equations, from 1 and 2 we can easily convert from ASA to ORS. They ask sometime questions on this. So if you remember the matrix formulation, then you substitute the values of CS. If he gives lambda, then you can use substitute lambda values and then get the CS, substitute CS and inclination and alpha. You will get the values of alpha, back rake angle, side rake angle. This is one, you should remember the formula. There is no other way to remember this. That's about angle, orthogonal angles, ASC system and geometry of the tools. Next one is orthogonal cutting. Different types of cutting. So we have cutting tools. Suppose we take only single point cutting tool. Multi point cutting tool we won't consider for all these calculations, and we study only single point cutting tool. Multi point cutting tool will become it's very complex to understand as per our standards. Two types of machining, methods of machining. First one is orthogonal machining, orthogonal cutting. etching or cutting, or two-dimensional cutting, 2D cutting. So in orthogonal cutting, the cutting edge of the tool is perpendicular to the cutting velocity or feed direction. Cutting edge of the tool is perpendicular to the cutting velocity of the tool. In orthogonal cutting, the cutting edge, this is cutting edge and this one is a tool, and it is moving this is the workpiece direction of the cutting tool. If you look at the diagram, the cutting edge is which is perpendicular. So this is cutting edge. Cutting edge is perpendicular to the direction of the cutting tool. So here it is also called two-dimensional. It's only x and y axis considering, and because two-dimensional it is also called only two forces will act, cutting force and thrust force. Orthogonal or oblique cutting tool. In oblique cutting is also called three-dimensional cutting, where cutting edge is not perpendicular to the cutting velocity. Cutting edge is not perpendicular to cutting velocity. Here it is also called three-dimensional cutting. It has three velocities: cutting velocity and two thrust velocities, horizontal and vertical thrust. So three major differences are, just write out the difference between the orthogonal and oblique cutting. In orthogonal cutting, as we mentioned, cutting edge is perpendicular to the tool direction. Here in oblique cutting, cutting edge is inclined is not perpendicular. Cutting edge to the tool direction, to the direction of the tool feed or tool motion. Direction of chip flow velocity is perpendicular to the cutting edge of the tool. Another way of orthogonal cutting definition. Direction of chip flow velocity is perpendicular to the cutting edge of the tool. Here the direction of chip flow velocity is at an angle. Direction of chip flow velocity is at an angle of to the cutting edge of the tool. Another major difference is two mutually perpendicular components of cutting forces act on the tool. That's why I mentioned two-dimensional cutting. Two mutually perpendicular components of cutting forces acts on the tool. Three components of cutting force acts on the cutting edge and they are mutually perpendicular to each other. Three components of the cutting force acts on tool, and these three are mutually perpendicular. So that means three-dimensional. Maximum chip thickness may occur at the middle. Their maximum thickness occurs in the end. Example: jack plane. If you see in carpentry, they use jack plane. Broaching is example. Here example is lathe turning. Drilling, milling, shaping, all these are all general used. Only jack plane and broaching are two-dimensional. Remaining most of the operations are three-dimensional. So that's about orthogonal and oblique cutting, and this is one of the important. Next one is types of chips. So in mechanical machining operation, there are different types of chips developed when you are machining different types of material. If you are machining brittle materials, you will get discontinuous chips. If you machine ductile materials, then you will get continuous chips. We discuss in detail all the three types of chips. Next topic is mechanics of chip formation. So when the forces applied by the tip of the tool on the workpiece, so example, this is a workpiece, this is a chip, and this one is tool. Just to understand layout diagram, this is chip, this is tool, this is workpiece. When the forces applied by the tip of the tool on a layer of the material such that the stresses induced in the layer of the material is greater than equal to ultimate stress developed in workpiece is greater than ultimate shear stress. If the stress is greater than ultimate shear stress, then breaking takes place. So here we are breaking the material, so the stress has to be greater than ultimate shear stress. The shearing is started at the tip of the tool and it propagates towards the surface of the workpiece, producing chip during machining. So once the it propagates to the surface. Similarly, it like layers by layer it removes the material from the workpiece. From this mechanism of the chip formation is due to shearing and tearing. So mechanism is shearing and tearing. Shearing and tearing takes place at the tip of the tool. So the propagation of shear towards the surface of the workpiece is called tearing. Plane in which the shear propagation is taking place is called shear plane. So this plane is called shear plane. In general, during machining of soft and ductile workpieces, continuous chips are produced because the soft material having higher toughness. Similarly, crack wave and energy wave is observed by the material and the crack wave will disappear somewhere in the center, maintaining the continuity of at the tip of the surface. Whereas during machining hard and brittle materials, the discontinuous chips are produced because they have lower toughness and allowing the crack wave to propagate easily to the surface, producing small chips or breaking the continuity of the chip. During machining soft workpieces, magnitude of energy wave is lower due to lower strength of the material. Energy wave can't propagate to the surface, whereas in the case of brittle materials, energy wave is larger because of higher strength of the material. Energy wave can propagate up to surface easily. Here we discuss about built-up edge formation. Adhering or welding built-up edge formation. Built-up edge formation. What is built-up edge? Adhering or welding of micro chips powder particles to the rake surface of the tool. adhering or